Welcome back. Today, we're diving into the chemistry of supermaterials. It's crazy to think about, but the simple act of combining basic metals creates materials that are infinitely stronger and way more versatile than their pure forms. We're talking about the science of bonding and alloys. This is an absolutely essential pillar for your O-level chemistry exams, so get ready. We're going to break down exactly how this works on a microscopic level.
So does mixing metals actually create supermaterials stronger than pure metals? It kind of sounds like magic, right? You take a relatively soft metal, mix it with another element, and boom, suddenly you've got the unbreakable framework for a towering skyscraper or the resonant brass for a trumpet. Understanding alloys is absolutely crucial. Grasping the exact mechanics of how pure metals transform into these supermaterials isn't just going to earn you critical marks on your exams, it's going to give you a real-world appreciation for the engineering that literally shapes our cities. Here's our roadmap for today's explainer. We'll start with an introduction to supermaterials, then cover ionic and covalent bonds. After that, we'll decode the metallic bond and explore properties like conductivity and malleability. Finally, we'll navigate some common exam mistakes and wrap up with a summary and a final exam tip. All right, part 1, ionic and covalent bonds, the micromechanics of electron transfer and sharing. Okay, let's track this step by step. Look right here at step 1. We've got a single sodium atom, and I want you to notice that label pointing exactly to its single outermost electron. Now follow that thick arrow moving into step 2. That arrow physically represents the complete transfer of that electron over to a chlorine atom. It's literally relocating. By step 3, they aren't just atoms anymore. They're oppositely charged ions. See how those visual boundaries lock them tightly together? That shows the strong electrostatic attraction forming sodium chloride. It's a total permanent transfer of an electron. Now compare that to covalent bonding. Here we have two non-metal hydrogen atoms, but instead of a transfer arrow, see how they overlap right in the center? These atoms are sharing pairs of electrons right in that intersection to achieve stability. Neither atom is giving an electron away entirely. They're holding tightly onto that shared pair between them, which creates a stable H2 molecule. And this split screen brilliantly illustrates the core difference. On the left side, we have ionic bonding. Notice how we've clearly emphasized the word transfer. One atom gives, the other takes. But look over on the right at covalent bonding. Here the emphasis is entirely on sharing. The atoms are physically overlapping to share those electron pairs. So transfer on the left, sharing on the right. Keeping these two mechanisms crystal clear in your head is step 1 to acing those chemistry finals. Moving on to part 2, the metallic bond decoded inside the sea of electrons. Let's zoom in and look deep inside a solid piece of metal. Pay close attention to the labels here. We have what's called a sea of delocalized electrons. These are the outer electrons that the metal atoms have actually let go of. Notice those little animated arrows showing the electrons moving completely freely, just washing around those larger circles? Well, those larger circles with the plus signs are the positive metal cations. Basically, the atoms lose their outer electrons, and those freed electrons become a fluid, stabilizing glue that holds all those positive ions together. Part 3, properties, conductivity, and malleability. How microstructures dictate macro behavior. Check out those arrows pulsing right across the structure. When we talk about conductivity, we are talking about exactly this movement. Because that sea of delocalized electrons isn't tied down to any specific atom, it can flow. When an electric voltage is applied, you can see those explicit directional arrows showing the electrons carrying that electric current straight through the metal lattice. That microscopic freedom of movement is exactly why this material can power your entire house. Let's frame this as a worked exam example. Why do specific elements behave the way they do? Looking at the table, we see that metals lose electrons. But what's the physical cause? Low ionization energy. It just doesn't take much energy to strip that outer electron away. On the flip side, nonmetals gain electrons because they have high electronegativity. That means they have a super strong pull to grab electrons and achieve a stable octet. Understanding the physical reason behind the behavior is exactly how you secure full marks on those tricky, long-form exam questions. Part 4, avoiding common exam mistakes. Navigating the exam pitfalls. So, here is an absolutely crucial rule you need to remember. Electrons are free, but the bonds are strong. We really need to debunk a massive myth here. A lot of students hear freely moving electrons and automatically think metallic bonds must be weak and loose. No way.
Look at those thick tension lines drawn between the positive cations and the electron C. The electrostatic attraction between those positively charged metal ions and the negatively charged sea of electrons is intensely strong. That is exactly why metals have such incredibly high melting points. Here's another major mistake we see all the time. Do not assume a block of metal is just a stack of neutral atoms sitting next to each other. Look at the split screen. On the left, that diagram of neutral atoms is literally crossed out. On the right, the green check mark highlights the reality. A metal structure consists entirely of positive ions suspended in a negatively charged sea of electrons. If you draw neutral atoms in an exam diagram for a metallic lattice, you are going to lose points. Always, always label the positive ions. All right, part 5, summary and final exam tip, wrapping up the chemistry of alloys. Let's do a quick recap of the core mechanics we've covered. Number 1, ionic bonding is all about the complete transfer of electrons and that resulting electrostatic attraction. Number 2, covalent bonding is about atoms physically overlapping and sharing electron pairs. Number 3, metallic bonding features that incredibly important sea of delocalized electrons washing around positive ions. And finally, when you mix different sized metal ions into that lattice, you disrupt the regular layers. This creates alloys, supermaterials that are dramatically stronger simply because the layers can no longer easily slide past one another. And that brings us to your final actionable exam tip. You have got to practice drawing these diagrams. Seriously, don't just memorize the words. Grab a piece of paper right now and practice explicitly drawing the circles, the plus signs for the positive cations, and the dots for the electron sea. And when you draw an alloy, make sure you show different size circles. That visually proves to the examiner that you understand how the mixed metal structure stops the layers from sliding. Visualizing the exact electron arrangement is the absolute key to mastering this topic. I'll leave you with this final thought. How will the unique chemistry of alloys continue to shape the future of the materials around us? From aerospace engineering to next-generation medical implants, manipulating that microscopic sea of electrons is literally what allows human innovation to push boundaries. If this explainer helped you visualize these concepts, make sure to like and subscribe so we can keep making these complex topics crystal clear. Keep exploring, keep questioning, and we'll see you in the next one.